as sulfides. So this also explains why we have such a low concentration of DGT of iron in the water there also. And then if we look at the other metals, compared to the other sites, we have lower concentrations of these elements in the pore water compared to the other sites, which means that these elements are also largely removed from the pore water as sulfides and are not available. So also here, if you use the flux, the concentration gradient, we will see an important flux from the overlying water to the pore water. So just some conclusions. Our sediments are good records of long-term pollution records and are less affected by changes in the concentrations over time on a short time scale. We have quite high concentrations, especially in this upstream area of the New River at the Hanoi area. Some elements also have upstream enrichment related to the Red River. So our statistical analysis can show our distribution patterns and connectivity between the different rivers and the ponds and the downstream transport. Our DGT in water shows a good correlation between the particle and dissolved distribution, so that shows the importance of colloids on this DGT labile fraction, which is higher. This DGT labile fraction is higher for the oxyanions compared to the trace metals, and especially for arsenic, the sediment can be an important source to the overlying water. So that we have to still calculate the benthic fluxes, where we have the data for to do that. Okay, so this was the end of my presentation. Thank you.
Thank you very much, Martin, for a very interesting presentation, and I see the good result from our previous project. And okay, so if anyone have questions, we can have time for one question, then we have to move on because the time is we are behind the time schedule. Okay, so actually I have a lot of questions for Martin, but not today, yeah? So we have to move on with the Dr. Vincent Perrot with his presentation, and the title is Mercury Speciation in Aquatic System. Please, the floor is yours, Vincent.
Hello, everybody. I need to share my screen, but I never use Teams, so I don't know how to do this.
See the arrow in the right-hand side, up in the up corner.
Yeah.
Yeah.
Yeah, it's good.
Can you see it?
Yes.
Okay. So hello, everybody. Thank you for inviting me to this nice workshop. So I'm Vincent Perrot. I'm actually a postdoc, and I'm working at the Vrije Universiteit Brussels under the supervision of Uwe Gao and Martin Leermerkers that are here. And I'm mostly doing my research on mercury fate in the environment. So how I'm going to do my presentation is first I'm going to talk about generalities of mercury cycle and the main sources and transformations that happen in the environment. And then I'm going to present some results we got of mercury speciation from the last 2 years in an estuary, the Scheldt estuary in the north of Belgium. So I guess you all know about mercury. That's a heavy metal, so I'm going to go quick on that. It's a very unique element, as you know, compared to other trace elements. And the feature is that you can find it as a volatile species in the atmosphere. mostly as volatile species. It can be oxidized too. And then in water systems or soils, it will be oxidized mercury mostly. And this mercury 2+ will be in the aquatic system either as dissolved or bound to particle. And actually, if it's bound to particle in the water or if it's in the soil, it really likes to bind with organic matter and sulfur, which we will see later that it's an important feature. And also it's a very toxic element, and the severity of the toxicity depends on many factors, such as the chemical form, the dose, exposure time, and the way you uptake it. So actually, mercury exists mostly as a cinnabar, and it's been mined for a long time. And actually, you can see here on this map that like 75% of the mercury comes from like major mercury belts, which the two mains are actually in Europe, the Almaden mine in Spain and another one in Slovenia. So you also know that mercury has been used since actually before, I mean, in the antiquity, such as Romans that were using it for vermilion pigment, and it's been largely used also for silver and gold mining. And in more modern times, it's been used for a lot of commercial products. And eventually, countries started to regulate its use after the Minamata disease in Japan, that you probably know also. And they have banned its use for several things. So here is kind of a summary of like the last 150 years of mercury use. So you can see all these uses, and you can see first a big peak that is due to the gold rush in 1850, and then it started to appear with a lot of other things. And after use or during use, this mercury is then released to different Earth compartments, and it's quite like well reported between the air, the soil, water, and landfills. So that's mercury release in the environment due to specific use, but you also have a lot of mercury release that is like unintentional or is like a byproduct of other activities such as fossil fuel combustions or lead, zinc, or copper smelting. And actually, you can see that about 200,000 tons of mercury have been unintentionally released to the environment. And one of the main sources nowadays of unintentional mercury is coal combustion. So it's not only a problem for CO2 emissions, but also for mercury. So here you can see that at the beginning, the CO2 emissions were mostly due to coal, but it started to decrease a lot since the amendments of like other fossil fuels such as the petroleum. But since the 1970, the share of coal started to stabilize. And actually, if you compare those two profiles, so that's the mercury release from coal. So here you can see it from the different countries. So you can see that before 2000, it was mostly from Europe and North America. But developing countries, especially in Asia, started to use a lot of coal, and so they released a lot of mercury from this use, in which the vast majority was released to the atmosphere. So yeah, you can see those two profiles are actually quite similar. So you can kind of correlate CO2 emissions and mercury emissions from coal. And you can see that in 1950, about 150 tons were released. 150 tons of mercury were released, and in 2010 is like 1,000 tons. So if you go back to history, you can see that most of the mercury was released after 1850. So you see the gold rush here, they were decreased because of the world wars, then used in a lot of processes, and then start to controls So the mercury started to decrease, but the increase of coal use and also the artisanal gold mining actually made the mercury emissions to increase again in the beginning of the 21st century. You also have natural sources that are biomass burning, volcanoes, and also soil erosions, because our soils contains trace amounts of mercury. Global average is about 80 nanogram per gram. So you can see the biomass burning originates mostly from the South Hemisphere, and you also have a lot in South Asia. From volcanoes, it's also an important source. It's about 20 to 40% of natural emissions. So you have emissions for passive degassing, but also from a large volcanic eruptions, which does not happen a lot, fortunately, because when they happen, they release a significant amounts of mercury that you can see the last 3 big eruptions here. So the Tambora and Krakatoa in Indonesia, and then in Mount St. Helens, those peaks of natural mercury are actually stored in archives such as ice core, but you can also see that in sediments, for example. So basically, already at the beginning of the 2000s, people started to make models and compare flux and storage of mercury, the different Earth reservoir between the pre-industrial times and the actual times. And you can see that actually since the industrial period, about 2/3 of mercury emissions are actually estimated to be due to human activities. And the stock of mercury in some reservoirs, such as atmosphere and oceans, are significantly increased. So of course you have a mercury sink, which are the burial in deep sediments, but it takes more than centuries to do that. Whereas the mercury resonance times in the atmosphere, where it's mostly emitted now, it's only 0.5 to 2 years. So eventually you have constant increase of mercury in those reservoirs. So here is most updated thing, but it's similar to these graphs. So it was done by Outridge et al. In 2018. So you see that the increase of mercury in the atmosphere is about 500% since the industrial times. Also in the surface oceans, big increase, and still significant but smaller in organic soils. So these increases in the different reservoirs also are connected to increase in fluxes between those different reservoirs. So you could see here deposition to land and fresh waters and oceans has increased significantly, and opposite fluxes, which are evasion, also increased a lot. So now I'm going to talk mostly about mercury transformations in the environment. Sorry. And we will focus especially on speciation. So the speciation is actually the different forms that mercury can get in the environment. It can be gaseous, dissolved, or particulate, inorganic or organic. Organic would be the methyl mercury, or it can be oxidized or reduced. So in the atmosphere, mercury is very reactive towards a lot of parameters. And that's the same in natural waters. And what's important in waters is just the transformation of inorganic mercury to the methyl mercury, which is highly bioaccumulable. So here you can see all the main transformation that can happen. So you have the mercury in the atmosphere mostly as mercury zero, but it can be oxidized. And once it's oxidized, it can deposit to land or water systems. And once in those water systems, it can be reduced back, go back to the atmosphere. It can partition between the particle and the dissolved phase. And in it can be methylated or demethylated. The demethylation can involve direct transformation to mercury zero. And then what's important here is the methyl mercury that has a high capacity of bioaccumulation and biomodification. So here is the atmosphere. I'm not going to go in details in that, just to say that it's very complicated to study mercury in the atmosphere. even if it's very important, because there are very, very low concentrations, especially in uncontaminated environments. And there are very, very different transformations that can happen, for example, on aerosols that are not really known until now. Here are maps of the global distribution of mercury and the surface atmosphere. So basically, you can see that they are important mostly in the northern hemisphere close to the industrial area. So especially in China here, which is due again to coal use. And then here you have the flux of mercury depositions, so to land or aquatic systems, and you can see that it's actually naturally related to the concentration at surface. But most of the mercury in the atmosphere is high in the north hemisphere, but the deposition is quite well distributed. I mean, it's not well distributed, but it's not related to the surface concentration. And basically, you have more deposition of mercury when you have more precipitation or wet deposition. Here you have a map that combines models and measurements of mercury in the oceans. So you can see here, it's not like in the atmosphere, but it's close. It's very, very low concentrations. So you need very clean techniques of sampling, and you need very sensitive instruments to measure it. Okay, so actually, when you're far from like very local and important source of mercury discharge, the main source of contamination to humans is the consumption of water life, basically seafood. So since as the mercury in the waters are mostly as an inorganic form, like 99% of mercury will be inorganic. At the end, in the food webs, you will get mostly methyl mercury. And so this is due, as I said before, to methylation. And that's a very important transformation because it will eventually control the amount of mercury that will be stored in the food webs. So here again, I put a cycle of mercury. Yeah. So basically, when you are in aquatic systems, you have runoff and wet and dry deposition that actually put mercury in your system, and then it can be methylated. So what will control mercury accumulations will be methylation versus demethylation, or the net methylation. And as you can see, in the water column, you have mostly inorganic mercury, but the further you go in the food web, the lower inorganic mercury you have, and in contrast, the highest methyl mercury you have. So methylation is mostly done by microorganisms in anoxic environments, and it's actually believed, it's not believed, it's been proved that it's done mostly by sulfate-reducing bacteria, but it can be also done by some archaea or ferry-reducing bacteria, and only, even if this is known since the beginning of the 80s, that sulfate-reducing bacteria are the main methyl mercury producers in waters. Only in 2013, people have identified the two genes that are responsible for methylation, because before it was not known if it was accidental or not. And so it was work of Parks et al. In 2013, and they identified two genes from a certain bacteria that are able to methylate mercury. And then what's important also is that not all the mercury, so inorganic, will be available for methylation. It needs to be in a specific molecular forms, but it also depends on the bacteria, the type of bacteria. So you can see that you can have different way for mercury to get in the bacteria and then potentially be methylated. So you can have a MER-based transport, which is encoded by genes. You can have active transport that may be triggered by some specific molecules that the bacteria can generate. And what actually is used by DGT is just this process of passive diffusion, which is the diffusion of uncharged complexes. So those uncharged complexes are lipophilic, so they can easily cross the membranes and get then into the microorganism. So the opposite reaction of methylation is demethylation, which can be also done by microbial activity. So you have two types of demethylation by microbes. You can have oxidative methylation. So it's not called oxidative because the mercury is oxided, because they are in both the methylmercury and the inorganic mercury is 2+. It's oxidative because the product of the reaction will be CO2 in this case. In the other case, it will be CH4. So it's the reductive or oxidative is for the carbon, not for the mercury. But anyway, the oxidative demethylation is usually done in uncontaminated environment, whereas the reductive demethylation is mostly done in contaminated environment. And on this graph here, so some people have studied the different typical strains that are known to methylate mercury, and you can see that those strains are actually also capable of demethylation. The methylmercury degradation can also be done by sunlight. So, but this degradation will depend on the type of sunlight, and also the mercury that is bound to organic matter will generally be much more photodegraded than other mercury. And the type of organic matter is also very important. As you can see here are different kind of thiols. So thiols are like reduced sulfur groups from the organic matter, and that's what mercury like. Remember, mercury exists mostly as a cinnabar, so that's sulfur, mercury sulfide. And so mercury likes a lot the sulfur group, reduced sulfur group. That's why we call this element chalcophile. So you see that the type of organic matter will import the concentration. And also what's interesting, and that you can see that under chloride environment, it looks like the photodegradation of methylmercury is prevented. So when you look at mercury in seawater, it can be an important thing to take into account. And you can also have reduction of mercury 2, which will be a process that will prevent mercury 2 to be available for further methylation. And this again can be influenced by a lot of parameters, such as humic substances. And also you can reduce the mercury, not the methyl, but the inorganic, by a sunlight activity. And then the last reaction will be the oxidation of mercury 0. So you can have mercury 0 in the waters, and it can be oxidized by thiols in general. So thiols are involved in both reduction and oxidation. And again, light has an influence on oxidation. And apparently also chloride has an influence of oxidation. So that might be why, as I showed before, actually they observe lower photodegradation when you have high chloride concentration. It might be just because you have more photooxidation. So that's the balance in between. As I said before, mercury likes a lot organic matter. And you can see on the first graphs on the top, so there are like different organic matter. So that's organic matter isolated, for example, from a river in the United States, but whatever. And you can see that the dissolution rate of mercury bound to sulfide, for example, will be promoted by some specific organic matter, and their molecular weight, the aromaticity, or the absorbance of UV light will actually be very important controlling this type of dissolution. Some other groups also have shown that the bioavailability of mercury also depends on the type of organic matter you are bound to. For example, here you can see that the methyl mercury that was found in plankton was actually decreased if you have more organic matter that come from terrestrial sources. That's also something that you can see here. And in the opposite, it looks like that the mercury bound to more marine organic matter will be more easily available. So to summarize this, you have multiple mercury sources in the environment, multiple transformations of this mercury, which is influenced by a lot of different parameters, and this will determine its speciation in the aquatic environment, so between particulate or dissolved, gaseous or aqueous, organic or methyl mercury or inorganic mercury, and this will actually influence the bioavailability and eventually the bioaccumulation. So when you sample mercury in the natural environment, you will have an information of where the mercury comes from, but not necessary because it's just sampling at a time t and on a specific type of samples. So the best to understand what's going on is to combine sampling of different type of sample that can give you more short-term or long-term informations. I'm not going to talk a lot about analytical tools and process to measure mercury, but just here. So for example, if we want to get the methyl mercury out of a soil or a sediment or organism, we do extractions with what we call soft extractions. So it's nitric acid, but only 50%, like 6 molar, which prevent the carbon bond of methyl mercury to be broken. So you actually preserve the mercury species. And after that, you need to derivatize your species with what we call a derivatizating agent, which is basically getting those mercury species volatile by putting ethyl group bound to it. And then after that, you can purge it into a system. So that will separate the methyl mercury from inorganic mercury through a GC, gas chromatography, and then it will be detected by atomic fluorescence spectrometry. So that's the instrument we have now at VUB since last year. And there is another way to do that, which is actually a bit more accurate, is to do the same, but adding enriched tracers in your natural samples, so you can actually correct from analytical artifacts such as the methylation or methylation actually during the analytical process. So that would be more or less the same process, except that you actually make those ethylated species to go in an organic phase, and then this organic phase will go to a GC. And since you use enriched isotope tracers, you cannot use IFS. Of course, you have to use ICP-MS. So what people do is that they usually couple gas chromatography with ICP-MS. So here you can see the oven of the ICP-MS. You have a transfer line. The oven of the GC. You have a transfer line, and you also inject a standard here in the meantime, and then it gets detected in the ICP. And then you can deconvolute the signal between what is from your sample, and what you added as enriched tracer. And from this way, you can deconvolute and get back to your concentrations in your things. So yeah, now I'm gonna talk about some results we get from an estuary, as I say, the Scheldt estuary. So it's we focused in this area. So it's actually at the border between Belgium and Netherlands. And this is quite a big basin. So the drainage basin of the Scheldt estuary is about, I think, 20,000 square kilometers. It has a length of about 360 kilometers. And this river goes through a lot of agricultural, urbanized and industrial area, especially in Antwerp. So that's the sampling station. We just went through to sample mercury. So we started here just before Antwerpen, which is a big city, the second city in Belgium. And this Scheldt River is like surrounded by a lot of different things. So here you have the water treatment things, but you have waste incinerators that are here that release a lot of mercury. You have oil refineries, steel factories, cement factories, all that is supposed to release mercury, and a lot of petrochemical industry, because actually Antwerp is one of the biggest petrochemical complex in the world, second one after Houston. Yeah, I'm not going to describe that, but basically all the industry, all the petrochemical industries that exist in the world, they have at least one factory in Antwerp. Oh yeah, and you have a power plant, a nuclear power plant too. So anyway, so we went to sample 2 days in March 2020 and 2 days in March 2021 under the research vessel Belgica, and we collected water sample and sediment sample at these stations. We also collected the water and sediments in the North Sea, but today I'm just going to talk about the mercury between this place, which is about 100 kilometers out of the upstream, and this place, which is the mouth of the estuary. We also sampled sediments and water in this canal, which also discharge in the estuary, but I'm not going to talk about it. So the samples for the water, we sampled from the Zodiac that was linked to that was just on board, and we could not, it was easier to avoid contamination to get on Zodiac to get the water, because the boat can contaminate the sampling, especially for mercury, which has low concentration supposedly. And back on the, after collection, back on the board, on the boat, we filtrated water sample to get the dissolved and particulate fraction of mercury. And for the sediment, we sampled them directly from the boat with a box core. And then we cut the sediment cores into the sections. I put 2 millimeters here, but I think it was 2 centimeters. And then we did all the analysis, of course, when we were back in the lab, because we cannot analyze mercury on board. Here are the results. So all these profiles are from the distance from the mouse. So basically 1 point is 1 station, right? So HEM will be this one, the further from the mouse, and SO1 will be here. So here you have the 4 sampling dates, 2 in 2020, 2 in 2021. They were all at the same period in March. And you can see that both years and both days, conductivity and salinity are very reproducible, but some other parameters are quite different, such as temperature. Here you don't have the unit. It's actually the suspended particulate matter. And you see a big difference between 2020, where you have a high load of suspended matter, whereas which is like higher upstream and lower downstream, and it was not the case in 2021. pH also changed like quite differently between the 2 years, and we are still wondering what this is. It might be just something wrong, because usually So the pH of seawater is around 8, that's fine. And historically, the pH is a bit lower upstream the estuary. But in 2020, we found the opposite, and we cannot explain that. Anyway, and yeah, and for dissolved oxygen, which might have a very important, can be very important into changing mercury speciation, especially methylation, you have quite difference between the 2 years. And so here is the mercury. So here you have the mercury bound to the particle. So that's the concentration of mercury on a particle. And you can see that it's quite high upstream and decrease sharply in the middle of the estuary to obtain the minimum value in the lower estuary close to the mouth. You can see small differences still between the 2 years, where the peak was in 2020 was in the middle of the estuary. Here is what they call the maximum turbidity zone, whereas in 2021 it was highest here in Antwerp and then started to decrease. So here you have another way to show particulate mercury. It's actually the concentration of mercury bound to particle in water. So it is actually a function of the concentration of mercury in particle, but also the concentration of particles in the water. So that's why you can see, for example, in 2020, a very nice similar pattern between particle concentration and mercury in particles. But you don't see that in 2021. And then when you look at mercury dissolved, then you see very big differences between the 2 years and between actually the 2 days in 2 years, in the same year, sorry. And in general, so here you have the KD, which is the affinity of mercury towards particle versus dissolved phase. So highest KD, that means higher affinity for. Sorry?
No, nothing
Hey.
wrong. Go ahead. It's just the noise.
Okay. So KD, in case I think you know, but anyway, if you have high, you have higher affinity for particle. If you are low, higher affinity for dissolved phase. So you can see a global decreasing trend between upstream and downstream. And here I have put the average for the 2 years and the 2 days each year. So here is an average on 4 measurements. And for KD and mercury concentration of particle, it's quite clear. Oh, so I changed the scale here. It's not the distance from the mouse, but it's from salinity, but it's quite the same because the salinity increased gradually from upstream to downstream. So yeah, for both KD and mercury and particle, it is clear that you have an increase a decrease from upstream to downstream where the salinity is higher. But as I showed just before, and for the total mercury dissolved, the dissolved phase, you see no correlation with huge variability between the days or the years. We also measured the carbon and nitrogen on those particles. And so you can see here that's particulate organic carbon, particulate nitrogen. So again, if I come back here, you can see that they follow more or less the suspended material concentration. But the percentage of carbon or nitrogen on the particulate matter vary very differently between the 2 years, right? Same for the isotopic composition of nitrogen, but for carbon, clearly for all years and both days at each year, you have a nice increase of this delta value from, so again, upstream to downstream. So if you are not familiar with this nomenclature or what can mean carbon and nitrogen signature, I'm going to talk mostly about carbon. Actually, carbon isotope signature can give you information of what is the source of this carbon. So basically, if it comes from terrestrial environment, it will be mostly depleted. And if it's carbon produced in the marine environment, it will be mostly and less depleted or enriched compared to this one. And if you compare that to mercury, you see a clear trend, especially in 2021, between the amount of mercury in the particle and the carbon isotopic signature. So remember, more depleted carbon in 13 means more terrestrial or riverine source. And then here, more marine source. So it's obvious that the source of mercury to the estuary comes from either, or actually both, the river and all the material that have been carried from the drainage basin to the river. So high mercury inputs were from the river and drainage basin to the estuary, and then following the salinity gradient, it will progressively mix with organic matter of marine origin, which contains, fortunately, less mercury. Then we compare these mercury concentrations from historical data. That is done like frequently by a team, the Scale Monitor, and they are from Netherlands, I think. And so here is the historical data. So you can see that for 4 stations. So we took SO1, SO4, SO7, and S12. You have a clear decrease since the 90s to 2018. And here are our measurements. So we are still seeing this significant decrease, but actually we don't see such a high decrease as expected, because for all of them we should be around here, and this one is quite high, especially also for the SO7. Like it looks like we're same level than 2004. So it's less decrease than expected, but it's still consistent. So it is clear that the mercury contamination in the Scheldt estuary has decreased compared to 30 years ago. So here are the dissolved mercury profile. So remember that I'm just presenting 2021 here, because we have 2 big peaks, and also in 2021 we were able to measure 2 different fractions of the dissolved mercury, so the total dissolved and the what we call the reducible dissolved, which is actually the mercury that will be weakly bound to organic matter, for example, weakly bound or not bound. And you can see, so the reducible will be a proxy for, let's say, labile mercury and or potentially bioavailable mercury for microorganism. And in both days, so you can see that you have the magnitude of the peaks are different, and they are not at the same place, but there are still quite 2 big peaks, and you have a significant fraction of mercury in this dissolved phase that is reducible. That means potentially bioavailable to enter the food chains, and hence also for being methylated further by microorganisms. And here I just put the total dissolved mercury versus reducible mercury, but not only in the Scheldt, but also in the Belgian coastal zone here, and in the canal here. And in any situation, you can see that the more dissolved mercury you have, the more reducible mercury you have. So that is naturally a good news, because that means potentially a lot of mercury could be available to the microorganism and then the food chains here. And also, I do not show the results, but if we compare to the studies from Martin Learmakers that was done in 2021, no, sorry, 2001, actually we have the same values of dissolved mercury than like 20 years ago. So whereas the mercury bound particles have significantly decreased during the last 20 years, this is not the case for dissolved mercury. So we also know I'm presenting the mercury that we got from the sediments. So we just did it for one station. Actually, this is a study we did with a master student from Vietnam this year. So what we did is we took these sediments from the station S15, it's right here, and we measured total mercury concentration using this AMA 254. So it's a very simple technique. I think Martin mentioned it in the previous presentation. It's based on atomic adsorption spectrometry. It has no chemical preparation. You just put your dried sample in the instrument and it gives you the total mercury concentration. We did some extractions then, as I presented before, to measure the methyl mercury in those sediments. We also tried to estimate the organic matter concentration, and we did some carbon and nitrogen isotopes also. So here you see the profiles. And then we did selective extractions, which is the idea is to determine the different phases that mercury can bind in the sediment. I'll show that later. So here you see the profile. So you see that for 20 centimeters, they were cut in 2 centimeters. And you have a strong decrease of mercury here around 15 centimeters, and then it decreases again. The methyl mercury is following the same pattern as total mercury, but the percentage of methyl mercury follow a quite opposite pattern. Interestingly, and as expected, you can see that the percentage of organic matter that was obtained by a loss of ignition is very close to the trend for total mercury or methyl mercury. Of course, organic carbon also show the same thing, because organic matter is composed about like half carbon. Like you see a mirror pattern for carbon 13. And then here you see the nitrogen and the ratio C on N. We can also give you an idea of organic matter processing, but I'm not going to go into those details. So I'm coming back to this methyl and total mercury. So as I said, you see the profile between total mercury and methyl mercury are close. And then you see here that actually the percentage of methyl mercury is higher while the total mercury is low. So here you have the total versus organic carbon or versus isotope composition of the carbon, and such as we have seen from the water samples, you have nice correlations between the percentage of carbon or its isotopic composition and the amount of mercury, right? So that means when you have more signature of carbon that is more from terrestrial or riverine sources, it has higher mercury concentration. When you go to marine signature, it has lower concentration. So as you can see here that the methyl mercury is quite correlated to the total mercury, but if you take the percentage of methyl mercury, it is actually negatively correlated to the amount of total mercury, and this can be due to the fact that if the mercury is mostly bound to carbon, then it will prevent, or to organic matter, it can prevent methylmercury formation by preventing bioavailability. So here are the selective extraction results. So basically what you do is like you apply a chemical treatment with different reagents to your sediment, your dry sediment, and these specific chemicals will extract mercury bound to a specific fraction, such as carbonates or exchangeable mercury, which will be the most bioavailable one. Then the mercury bound to specific types of organic matter, which are humic and fulvic acid, some residual organic matter, mercury sulfide, or oxides. So here you have it as a mercury concentration, and here is the profile with mercury fractions, percentages. And you can see that in any depth, you still have low but significant percentage of mercury bound to the exchangeable fractions, the potentially bioavailable one, and those percentage more or less correspond to the percentage of methylmercury that we found in the sediment. So it might be that these carbonate and exchangeable fractions are the main responsible for methylmercury formation. That means the mercury is like weakly bound and can easily go into the microorganism or getting methylated. And I'm just gonna talk now about small experiments we did in the lab with DGTs. So the goal was to assess the, as you know, the DGT goal is to assess the bioavailable fraction of elements in water, or the labile fraction. So here for mercury, so we deployed the DGTs in different solutions for a long time and with quite low mercury concentration. And the main question we had is that since to estimate labile concentration of mercury in water, we use this DGT formula that is based on diffusive coefficient. The question was, what should we use to estimate these concentrations in natural environments? What D values should we use? Because you know that mercury likes to bind with organic matter, but depending on the type of organic matter, you can have a very different diffusive coefficient value. So that will, if you use the wrong one, you might get very inaccurate in estimating the labile fraction of mercury in those waters. So we decided to deploy those DGTs in seawater with different mercury and organic matter concentration, using also different type of organic matter. We use like pure humic acid, and we use natural organic matter that was a terrestrial one. And for some experiment, we did not spike with mercury, so that was just like a natural concentration from seawater we collected in the harbor. So a couple nanogram per liter. When it spiked, it's more like 500 nanogram per liter. And interestingly, in all cases, you can see that as a function of time, the mass of mercury accumulated on the resin was linear, but depending on the experimental conditions, that means mercury on organic matter ratio, for example, you have very different slope coefficients, and those slope coefficients are related to the diffusive coefficient. So then we decided to plot the percentage of dissolved reducible mercury. So remember, reducible mercury is the one that will be the most bioavailable or labile, versus the calculated diffusive coefficient from these lines. And we can see a quite good correlation between the percentage of dissolved mercury in the water and the diffusive coefficient that was calculated from the experimental data. So maybe since if you go in the environment in a river, it will be very difficult to know what kind of organic matter you use. Maybe if when deploying DGT, you also measure total and reducible mercury fraction in this water, you can have a proxy for what diffusive coefficient you should use, and you might reduce uncertainties in estimating labile mercury concentrations. Oh yeah, I'm not sure I have time for that, so I'm gonna go to
Better short it a little bit.
Yeah, that's why I'm going to the conclusion directly.
To wrap it and yeah.
So yeah, so mercury cycle is still not very well understood because of a lot of sources, a lot of re-emissions, a lot of transformations, methylation, demethylation, reduction, and sorption, desorption with organic matter and particles. So we still need to better constrain those sources in transformation, and it's especially important in aquatic ecosystems, because that's where mercury speciation mostly controls its bioavailability. So the idea is to combine field studies and laboratory experiments. I have not talked about mercury isotopes, but the use of isotopes, either mercury or others, carbon, nitrogen, can help to better understand and constrain transformations. And of course, the use of specific speciation sampling techniques can be a good idea to estimate the bioavailable inorganic and methyl mercury fractions in specific waters. And also because this technique is actually, it's not like at time t, but you can, since you have low concentrations of mercury in waters, you need to deploy DGT for 3 weeks, at least to get enough mercury to be analyzed. And so there will be a time integrated mercury bioavailable fractions. So this actually to better implement regulations in policies in terms of mercury emissions, remediation, and guidelines for seafood consumptions mostly. And the last slide I wanted to show is what's going to happen in the future in this context of climate change, because if you have an increase of temperature or change in like precipitations or humidity in the soils, those can really affect the mercury fate, such as the depreciation rate or the methylation rates. If you increase the temperature, you might have more microorganisms that can methylate the mercury. And then you will change also the flux between the different compartments. Here is a study that has been like published just recently, and people like show the methyl mercury concentration in seawater. So it's in femtomolar, so it's very very low. It's 10 minus 15. And here, depending of what's going to change, you can see the increase or decrease of methyl mercury concentrations. And so in some areas, especially in Antarctic and Arctic, you can have a 100% increase. And other factors such as thawing of permafrost or increase in forest fires can also actually increase mercury fluxes or release from a storage place to a place where it can be available for food webs. And I'm not even talking about land use change, which also can affect the mercury fate in the environment. So yeah, that would be my presentation.
Okay, thank you very much for your very interesting presentation, Vincent. Indeed, it's very new for us here, and also we have a lot of problem with mercury pollution in Vietnam, but we don't have the facilities to analyze the methyl mercury here. That's the reality. Yes, but I hope that in the future we can have it. And I also happy that Lien is working with you in this issue.
You know Lien.
Yes.
Yeah, Hong is Lian's Vietnamese promoter, huh?
Ah, okay.
Okay.
So
Yeah, she did a
when
very
Lian
good
goes
job
back,
actually in the
Lian
lab.
need to work for her, and probably Lian can continue to work on mercury field. I think it's interesting in Vietnam too.
Yes, because we have problem with gold mining here, and a lot of the gold mining here is artisanal gold mining, so
Yeah.
it's not possible to control the mercury pollution in this area. So actually, some years ago, me and Ding has also want to establish this kind of project with Norwegian partner, but unfortunately, we didn't success in this. But I still very interested in this issue, and I hope that in the future we can have the chance to deal with this in form of project. Okay, so thank you again, and I have to move on with Ding, because now you have just 5 minutes, Ding, to introduce your things.
Sorry for that, and all delayed from
Actually,
us.
this workshop meant for 2 days, but just due to the time differences between Belgium and Vietnam, so we have to squeeze this in only 2 afternoon here in Vietnam and 2 morning in Belgium. That's really pity for us. But I hope that the people made a interest when they are trained for us. And Ding, please, floor is yours. So you can introduce what you are talking about and why you are talking about this, please.
Okay, thank you. Can you hear me?
Yes,
Yes.
very well.
Okay, thank you. I just need a few minutes to introduce the Alliance for Resilient Urban Southeast Asia. Actually, last year we got a funding from UKRI in a scheme of Global Challenger Research Fund, and we are partnering with the British Geological Survey to get a funding for establishing a network of scientists from natural and science, and also from local authority to tackle the global challenges of urbanization in South and Southeast Asia countries. So the ARUSIA is UKRI GCIF Global Network for Resilience to Couple Human Natural Multi-Hazards with headquarters in our institutes at Vietnam Institute of Geoscience and Mineral Resources. So because I'm a geologist and we are partner with British Geological Survey, and this one is one of 20 network that bring together UK researchers with collaborators from across developing countries to tackle the global challenges. So we have the website, and we have the on the website at arusia.org, and also we have the Facebook fan page that we copy it in the chat box, so you can always access to our network. And I myself, I'm head of the Economic Geology and Geomatics Department of Vietnam Institute of Geoscience and Mineral Resources. I'm director of the network, and Dr. Payo Andres, head of Coastal Resilient Geohazard of British Geological Survey. He is also co-director of the network. And Dr. Nguyễn Thành Long, my deputy, he is manager of the network. As we are working on the problem of pollution, metal pollution in the urban area, So I think that the topic is well fit to our network. So you are always welcome to take part in to join to our network, to join the effort to tackle the problem of the urbanization and the problem of multi-hazard, and also the human-induced hazard that the people in urban area always facing now. So thank you very much. I just need just a few minutes for showing up our network. Thank you.
So thank you very much, Ding. Yes, as he said that we are all welcome to his network, because he also deal with every hazard, including natural and human caused hazard to our life. So this also his chance to introduce that workshop, that network to us. So if you are willing, and if you are feeling interest in that workshop, just feel free to join with him, with his network. Okay, so now we move to the discussion. Maybe it's a little bit late, but we let's say we let how to say 10 minutes for every questions if you may have to ask the present the speaker today. So feel free to discuss and to ask.
Hello, every people. Yes. First of all, thank you for Mr. Nguyễn Định for the introduction and sharing about information about the network. And my name is Nguyễn Ngọc Xuân Hải. I'm a lecturer in Thái Nguyên University of Agriculture and Forestry, and I work in faculty environment. And my research area focused on heavy metal, and I did my doctoral philosophy environmental remediation in Australia. So and I focus on heavy metal in committed soil in mining site, but in committed soil, committed heavy metal in water is my area. I looking for the opportunity and interested in, and as you present on the screen, so you have some people on in your network in University Hanoi, Đại học Mỏ Địa Chất. Yeah. So I really interested in your network, and I and my friend Mrs. Hoa in the same faculty and interested in your network, and we're looking for the opportunity to cooperation work, and maybe some further study. Yeah.
Thank you, Dr. Hai. As I said, that our network are open to everyone to join us, both from natural science and social science. And I think that the more we have in the network, so the more our ability to tackle the problem in the urban area. So thank you.
Okay. Okay. Mr. Dũng.
Yes, Chị Hương, can I have a question about the heavy?
Yes. Sure.
The mercury concentrations in the Đáy and rivers. I'm curious about the concentrations of heavy metal, particularly the mercuries in the sediment and the meters of the water level. I don't know the English terms for that, but perhaps that is the flow. I guess yes. I'm wondering about the concentrations of mercuries in the flows and in the sediments that you carry out and analyze.
Is Martin still there?
Yes.
Okay.
We only analyzed them in the sediments because for the water, the ICP analysis was not reliable for the water. We only have data of the sediments, and they are quite low, except in the area around Hanoi, which is quite high.
So there is only one area with quite high concentration in sediment, but all the others are quite low. So that's why for the second phase of this project, we didn't include mercury in, but we pay attention to arsenic.
Do you have the reasons for the low concentrations of mercuries in the station you sample?
The reason why they are low?
Yes. Compared to other places?
Yeah,
there are no important point sources?
No source of mercury contamination. Huh? That's good for you.
Are they low in the dissolved phase or low in general?
We didn't analyze water sample by using our instrument, but just use SVMS, but the results are not reliable. But they are low. We saw they are generally low. So
I can show the slide again if you like.
I mean,
it might be that the sediments keep all the mercury.
Okay.
The sediments are also not high. Eh?
No, we only have sediments and they are not high. So, there's only one point source, and that's these effluents in this new river.
Yeah. Yeah, the others
so there is
are
no contamination source of mercury close by to those areas. So that's good.
Right, exactly. But we expect to have higher concentration in the mountainous region where a lot of mining activity takes place.
Yeah, but even from Lian Tao Li, from the soil sample Tao brought with her, we did the mercury analysis. They are also below the Vietnamese standards. So the area where Tao got the soil sample, so seems mercury is not a concern, but cadmium is high. Yeah.
But I'm sure that if we go to
Actually, I have a question.
Yes.
Do you know if they are really use mercury for the gold mining in Vietnam? Because there are other techniques that you can use.
Right. Yes. It's sure. Many mining companies use mercury to attract the gold.
I think we just didn't go to the right area.
Exactly, because the area we have now is in the flatland and in the delta region, not in the mountainous region. But most activities of gold mining in the mountainous region, in the highland. Yeah.
This is a very small project. Financially, we also get a very limited budget. We cannot do everything to everywhere. So we focus on the rivers home proposed. So that's a little bit pity. Yeah.
But arsenic is a problem really in these river basins. And I saw that the concentration of arsenic in the fish is really high, and because I also want to discuss with Martin because I saw that the concentration of arsenic in the region 3 is not as high as compared to region 2, but actually in the fish tissue, the arsenic concentration is very high in region 3. So it must do something. It must how say there must be something with bioavailability of the arsenic in the region 3, because in the region 2, as you mentioned, that because of the high organic matter and maybe it's how to say the bioavailability of the arsenic is low.
It's possible. Mm-hmm.
Yeah.
And in area 3, you have also quite low oxygen concentrations, I think. So this promotes remobilization from the sediments.
So it is obvious that the bioavailable concentration is highly correlated with the bioaccumulation of metals in the organism, not the total concentration.
No.
It's very clear. So, Vincent, can you send us also, if it's possible, can you just send us your presentation after the workshop? Or it just...
Sure, no problem. Sorry, I was muted, but yes, no problem.
Yeah. Thank you very much. Yeah.
If my boss are okay with that, because there are some unpublished results.
Boss is here.
Yeah, but what is your decision? There are unpublished results, Vincent.
That's what I'm saying. So
just leave out the unpublished data and yeah. So.
Yeah. Vincent, I think that your presentation is very impressive, and as we are from Institute of Geoscience and Mineral Resources, I think that there are many opportunities for us to collaborate with you in the topic of the mining, gold mining, and also for the mercury pollution in the gold mine area, and also the topic of the mercury pollution in the estuary in Vietnam. I think that is also not yet studied now. Yeah, so I think that yeah.
You mean the Mekong? Am I right?
Red River and other river as well.
Okay.
Yeah, I mean that the long-term monitoring of the mercury pollution in the estuary area, and it's also affect into the food chain, especially in Mekong Delta and Red River Delta, where aquaculture are the mean of living for the local people.
Yeah. I guess there are a lot of fisher that like live on mercury. Either they eat it or they sell it.
Yeah,
it's their life, right?
Yeah, exactly.
Yeah. Yeah, that would be nice.
I think we have a lot of delayed, and is there any further questions? Because I have to leave in 15 minutes for another appointment, and I don't know. There are other questions related to this workshop and any topics. Go ahead and. But I need to discuss with you. I send my comments for TAO's result. You can have a look. You are in CC, and we should have a discussion separately. Soon, also some urgent aspects we need to arrange. For example, TAO's joined the PhD agreement and blah blah blah. So I think I need to talk with you soon, but separately, apart from this workshop.
Okay, so Let's do that. And okay, thank you very much for all of you who is still remaining until now for our workshop. So I also apologize for that extended
It's our fault.
beyond the schedule, but for me it's very interesting, and it's necessary that because a lot of issue and a lot of knowledge we have gained from this workshop. And if you don't have any question, and also other people also have the other duties to do, so we should end the workshop here. And once again, thank you very much for all of your attention during those 2 days. And I wish you good health and successful in the future. And I hope that we are here continue our cooperation. And everyone in this workshop, if you want to join with us, then we can find the opportunities to do so. Okay.
Okay, thank you very much. Thank you for all the attendance for this workshop, and we hope we can see all of you soon later in Vietnam or in Belgium.
So
difficult moments. And Martin, they cannot do sampling tomorrow because Vietnam is locked down now.
Yes, Vietnam and lockdown. Oh, that's a pity.
Actually, my place, only my place, there is a lockdown because of the F0 in the same place with me. So I am not allowed to go out of the building, and also other college also have the same situation. So I have to postpone it at least until next week, but I will manage the situation that we can go as soon as possible. So we will not waste the DGT you sent over to Vietnam. Yeah.
I think there's someone asking question again.
Okay, so Zoom, do you want to have another questions? The last questions?
No, actually, I just asked. I would like to ask about the fieldwork tomorrow, but Mr. Dr. Gao already informed us that no fieldwork tomorrow. So, I hope we continue collaborating with each other virtually, and hopefully we can. Yes.
Yeah,
Hopefully
who will update the information? I think.
Yes. Hopefully we can meet in person soon.
We have sent out our email to every attendance to announce that we cannot go to the field tomorrow, and then we will announce another with another email when the situation is changed for better. So be patient, please. So we will get back to you soon.
Thank you, Dr. Hương. And actually, I sent one personal email to you.
Yes.
Privately, and I hope you will get back to me.
Okay.
Yes. Thank you, all of you. And
yes.
We hope.
Thank you for your interesting questions and your attention to the workshop. I think from Belgium side, we wish all the Vietnamese friends Merry Christmas and Happy New Year. Yeah? Okay.
Okay.
And
Merry Christmas.
Thank you.
Happy New Year.
I really need to go. I really need to run now. Sorry.
Okay. Bye bye.
So see you. Bye bye. Home keep contact. Everything. Yeah. Okay.
Yeah, so keep contact.
Bye-bye.
Okay. Bye bye.
Merry Christmas. Happy New Year.